Hello, everyone in the audience. It's great that you could join us today. We're very pleased to have you here. So this is a very exciting colloquium because using large language models as the engine sort of behind agent-based modeling is a very fast-moving and interesting direction of research, which has only been made available by the advent of large language models. So I'll just first briefly say a couple of words about agent-based modeling and about tools that one can have to work with this framework within the Wolfram language. And then I'll turn it over to our esteemed presenters who have collaborated using a variety of programming languages. And so I will also show some tools that if you are a user of Mathematica and you would like to use any of the code that, let's say, is written in Python that any presenter might also be showing, then there's tools for you to be able to quite easily do that as well. So let's get into some of the additional resources that we have. So within that handouts tab that Rob's mentioned, we have some extra links here that you can use to both see the presenter's materials after the fact, download them and take a look at your leisure, as well as these additional resources that are available. So first, there's some Wolfram U resources. So if you're new to large language models in general, there's several great series that have to do with both using Wolfram language to call LLMs and write programs that involve calls to LLMs, and then others that are more oriented toward just learning about what is a large language model doing in the first place. If you're interested in creating custom personas for either using within a chat notebook interface or from a programmatic standpoint, there's courses oriented toward that as well. And one of the tools that I'm most excited to use for large language models is, of course, as a way to engage with students in classrooms. And in fact, one of our presenters that we'll have is going to be talking about that very topic. So in terms of working with large language models from within the language, so I'll briefly switch what I'm sharing here. So agent-based modeling is something that has been doable well before large language models, but typically one would either have to write rules or come up with some stochastic processes that these agents follow. One of the nice things about using large language models as the engine to drive agent-based models is that from their behavior they've learned from so much human text that they've ingested, you can get the stochastic behavior without having to necessarily worry about quantitatively coming up with what are the distributions that the agents should follow for given actions, right? You can engage with them in natural language and get things which one of our presenters will be speaking about. How well does this map on to what one would expect from experiments that have been done in the context of working with humans and many of these things that we use agent-based modeling to try to figure out how groups interact with one another. So if you're working with language models in the Wolfram language specifically, do you remember to check out the prompt repository as well as the tool repository for being able to both create and share prompts and tools that you're using to be able to easily add something to the community of users that are out there. Also, as I mentioned, if you're working in the field with large language models, many of your collaborators out there are going to be using Python libraries. And so there's a variety of resources available for running Python code right from within a Mathematica notebook. So for example, I myself am very much looking forward to using some of the great libraries that have been developed by some of our presenters today, just as easily as going to a cell for typing in a variety of other languages. So with the tools that are available for collaborating across programming languages and the community of researchers that are out there who are using large language models as the engine behind agent-based modeling, I think it's a really exciting time to be able to see, okay, what does this new way of easily creating agents allow us to research in terms of the interactions between humans and groups of humans. So without taking time away from our esteemed presenters that are here, so we're going to revert back to our original schedule. Our schedule of presenters that we have listed in the additional resources is what we anticipate. So this schedule is something that we'll be reverting back to Adrian going first, if you'll. So the presenters will be speaking for around 15 minutes on each topic, and then after the topic is gone through the structured part of the presentation, the audience will be available to ask questions, which we'll be moderating. If you have questions that extend beyond the 5-minute Q&A that's built in, please do feel free to continue to put those into the chat panel so that the audience can have their questions answered by presenters even after the official time slots have concluded. So without further ado, let's get into our first presenter, Adrian, who will be talking about an extension of work that was done at the Wolfram Summer School last year. And so I look very much forward to incorporating insights from many of our presenters into work that will continue on at the Wolfram Summer School for this year. So Adrian, thanks so much for joining us, and take it away.
Great. Thank you for the floor. I hope you can all see my screen and hear me, just to confirm.
Yes, sounds good.
Great. So, hi, I'm Adrian, and today I'll be talking about some of recent advancements on LLM-Agent simulations, including but not limited to scalability, context, as well as agent level and simulation level reasoning. So I work at the Artificial Intelligence Department of the Jozef Stefan Institute in Slovenia. You have my mail here if you would like to contact me after the presentation. So let's get right into it. So what was the state of LLM agents in 2023? So back in the summer of 2023, I partook in the Wolfram Summer School, where we developed some interesting first simulations using the LLM agents at the time. So what did these agents look like? So each agent was given a prompt, and inside this prompt was the entire structure of the agent in terms of what the different attributes and identity, actions, goals, and so on would be for that specific agent to make it unique. So the first thing we would include would be the identity of the agent. So you would tell the agent who it is, what its role is in the simulation, what its function might be. We would also give each agent different attributes. So some agents, if they're people, they might be slow, happy, hungry, and so on. Each agent within the scope of its simulation could perform a set of actions and ways of it would have different ways of interacting with its environment and the simulation. Moreover, based on the agent's identity, attributes, and the possible actions it could perform, each agent would have goals it would try to achieve using the aforementioned information. But to better do this, of course, each agent would have a log of its past interactions so that it would not repeat from its own mistakes and learn and get better. In some cases where the simulations were more complex, it also was very helpful to give the agents some few-shot learning prompts. So examples of how the agent could interact with the simulation and what actions it could perform. Although this proved to be quite a dangerous method of showing the agents what they could do, as tiny changes in the few-shot learning prompts could lead to drastically different behaviors of the agents in the simulations. Now, let's look at the actual simulations that we performed using this agent structure. So you can find our full Wolfram notebook and full investigation into these simulations at the Wolfram community. The link is also clickable on the presentation, which you should have in the presentation resources. So, but very quickly, we performed 3 different simulations, each of increasing complexity. So the first one was a simple rock, paper, scissors simulation. So we would have 2 agents, and there would be different, the simulation would be made up of multiple rounds. And in each round, each agent would either say rock, paper, or scissors. And then based on their output, we would decide the winner of each round. At the end of all of the rounds, we would tally up and see who the winner is. And of course, the agents will also have access to the history of the past rounds to see who won in the past. It was quite interesting to see here that GPT-4, when competing with GPT 3.5, was almost always superior in performance and always beat the GPT 3.5 agent, which was a quite interesting highlight of the importance of strategic reasoning, even in simple games and simulations like rock, paper, scissors. The next simulation was a sheep trading simulation. So here you can imagine 2 agents, and their identity is they're sheep traders with different characteristics. Some might be slow, some might be smart, some might be experts, and so on. And again, simulation was divided into a few rounds. We had a normally distributed sheep price that changed each round. Each agent at the start of the round would receive the current sheep price. They would also have a log of how many sheep they currently have and how much capital they have. And in each round, given all of this information, each agent could interact with the other agent. So there was 2 competing agents trading sheep. So they would have a brief interaction with free text, so 2-way communication, more or less. And after that, they would write down what their decision is for this round. Do they think that the sheep price will most likely go up or down in the next round? Then will they sell or buy or hold on to their sheep? And if they will sell or buy, how many will they sell or buy at, of course, the current price? So this was quite an interesting simulation in terms of seeing the disparity in the performance between GPT 3.4 and GPT 4 and GPT 3.5, as GPT 3.5 barely was able to grasp the simulation and was not able to give any decisions or interactions or actions or even interactions during the simulation that would seem plausible to anyone. For example, it would decide to sell 0 sheep or buy 0 sheep, despite numerous efforts to try and prompt it to give better responses or to give it a better understanding of the simulation, while GPT-4 was able to give very concrete and seemingly strategic responses, utilizing strategies like the buy low, sell high, without any prior specific prompting or instructions to use such a strategy. It was also interesting in the simulations how the actual identity of the agent did greatly influence the outcomes. So if you told an agent they're more scared and very conservative with their money and capital, they would also be less likely to trade sheep and sell them and so on. And the last most complex simulation here was the geopolitics negotiations. So here we had multiple agents, up to 10 agents at one point, but each agent was a country leader. So the agent was told it was given a full autonomy over a country. It was given different goals. So it had to optimize for different metrics like economic strength, military strength, forming alliances with other country leaders, and so on. Again, simulation was divided into several rounds. On each round, the agents first interacted. So each agent decided who they would like to interact with that round. They would then have a brief 2-way interaction with that other country leader. After this interaction, each agent would decide how to proceed in this current round, in this fictional world where they rule over the country. So they would describe their actions in free text. For example, we could have a fictional country, a fictional agent that's the leader of the, for example, United States. They would decide to talk to China. They would generally have some sort of interaction about forming alliances or trade agreements, or showing their military strength to discourage some other country from making any other aggressive moves. After this discussion, for example, the US leader might decide to, in fact, invest in their military strength to perform this joint military exercise and so on. And after that, so once each agent went through this process of, as described before, all of these prompts, or I guess descriptions of intention, would be taken, would be put together. Now, the problem was how would we take these different prompts and actually update the state of the simulation just based on free text? So at the time, the best solution we came up with was to have another sort of God agent. So, and this God agent would take all these prompts and would provide detailed reasoning for why they would like to update the simulation into the new state that it specifies. So, for example, if US and China decided to create a joint military exercise to show off their strength, they probably also invested in their military strength, perhaps, and other countries were also discouraged from doing anything. So perhaps this might be a plausible reason for their military strength to increase and the military strength for other countries to decrease, and so on. So, of course, this didn't work perfectly. There was a lot of complexity here that the agents were not aware of. But despite this, it was quite interesting to see how the GPT-4 agents tried their best to grasp this simulation and understand how they can operate within the constraints of the simulation.
Hi, Adrian. We also just wanted to check in that the audience shouldn't be seeing any additional graphics at this point because yeah, there.
Yes,
okay,
I'm on
perfect.
this slide. Yeah,
Perfect.
that's
Good.
all. So I'll quickly move on. So just a quick insight. So there was many insights from these simulations, but this is one of the examples. So the trading sheep, we can see that the wealth inequality greatly increased when the agents were encouraged to lie. So we can see at the top, when both agents are honest, they're ending their final wealth, so including their sheep and their capital at the end of the rounds of trading, was quite similar. While at the bottom, we can see two graphics where over 10 simulations were done, and we can see there's a clear disparity in the wealth inequality of both agents. Now, moving on. I see I don't have much time, so forgive me if I run over slightly. Let's talk quickly about what the different avenues of development are in terms of agent simulations today. So I'll briefly touch on 4 different points, including scalability, context, agent level reasoning, and simulation level reasoning to show sort of what the tools we are using currently are and what the technologies being developed include. Now, in terms of scalability, so very quickly, last year, it was quite costly to run discussions and simulations with 10 agents or more. Now, currently, this year, it is much more economically viable to run simulations including thousands of agents. This is in part one of the factors contributing to this is the fact that the price for the GPT-4 models and other similar LLMs are considerably cheaper by a factor of at least 100. Another important factor here contributing to scalability is being able to run a similar model similar to GPT-4, so Llama-3, a 7 billion parameter model is able to be run on a local laptop, so a high-end Mac, for example, which gives us much more freedom and autonomy and gives us less dependence on large corporations. So another potential here is potential application is the fact that we can use tools and the infrastructure is there for us to be able to run and actually support simulations of thousands of agents simultaneously, while also on the agent level, each agent can now run up to 500 tokens per second from various LLMs. But this is definitely a capability that is quite useful, and we are definitely using to maximize the agents. So we can run simulations very quickly now. Another quite important factor is the context window has increased. So each agent can, some LLMs can support context windows of 1 million plus tokens. So essentially this means instead of typing into ChatGPT a few thousand words and then having it act on this as an agent, you can give it quite literally 10 books, 10 full books, and have it act on based on this information. So all of these new capabilities allow us to create much more intricate simulations. Currently, we are working on the EU project TWAN, where we are modeling social networks using agents and humans, including several hundred agents and humans included, doing their best to interact and simulate a social network. There's also quite interesting improvements in the terms of the context that agents can have. So with the improved infrastructure and context length, as I mentioned before, we can now give agents demographic, psychological, and topical profiles taken from real-world forums, such as Twitter as well. Moreover, we can have real-time context retrieval. So we can take different context from external news sources and give this information to the agents live if they request for it, and they can take it, include it in their prompt, and do much more. Now, furthermore, even though the prompts can be potentially much longer with the context length, what we can also do is use retrieval augmented generation, which is a tool that effectively gives agents an almost unlimited access to different information that is relevant to the situation they're dealing with at the moment. So we can imagine the geopolitics agents in the previous simulation having access to all information known to the world and available online about a specific country, directly, locally, completely offline. Another thing we are able to do now is include humans in simulations with agents, because the agents can run quickly enough and generate text and receive context fast enough to be able to have humans live also included in such simulations. I know I'm running very low on time, so I'll quickly go over.
Actually, Adrian,
some of
you have another. Yeah, you have another 5 to 10 minutes. Yes, if there's any miscommunication about the time slot, you do have 5 to 10 minutes still, so don't worry.
Okay, great. I thought I had 10. Anyway, so let's look at some of the different things that we can do now on the level of improving the reasoning that agents can perform using all of the aforementioned technologies and tools that have now newly become available. So let's start with the understanding that agents can have of the different simulations and worlds that they interact with. So, for example, in this case, we give an agent running GPT-4 the story of Little Red Riding Hood. So this is a quite popular children's story. And we tell it, we give it the prompt above. So we wanted to describe the state of each agent throughout the story and to include the location, emotional state, intention, and the corresponding sentence from where the information was extracted from for every single agent in the simulation as it reads through the story and goes through it. So for example, here we can see at the start, the Little Red Riding Hood agent is located in the village. It has a normal emotional state. And this is based on the quite normal and neutral sentence of once upon a time, there was a little girl who lived in a village near the forest. And as the story progresses, you can quickly skim over and see that all of the other agents are also included where relevant, and their emotional state and location is updated accordingly. So sort of the insight this gives us is that agents do in fact possess the capability to understand complex environments, such as the real world, where you have villages, forests, different agents such as wolves, grandmas, Red Riding Hoods interacting within these environments with each other with different intentions and emotional states. So another way of imagining this is we have an LLM such as GPT 3.5, GPT 4. It has lots of information. It's more of a black box model. It's hard to know exactly how or which parts of the model are responsible for understanding something like complex simulation of the Little Red Riding Hood with agents interacting. But what we can do is we can try and get little white boxes within that model, so little localized areas of the model. We can try and tease them out to try and understand, to try and more explicitly and clearly define, formalize, and understand different aspects of these agents and their understanding of the world. So another way of phrasing this is we can try and get little local world models of these agents out of them, because as you might know, ChatGPT and GPT-4 and so on have a quite good understanding of the world and how different characters and agents in the simulation we like to call reality, or in fact not even a simulation. So they have quite a good grasp of such simulations. So now, how would we actually tease out these local world models from these agents? So let's take the example of a concept of having a motive to do something. So we can take this as some sort of concept that we all intrinsically understand. We can connect it also to different examples from our own past lives of where someone had a motive to do something. We also understand what a desire is, what a belief is, because these are sort of preconditions to understanding what this concept is. So we have all of this knowledge intrinsically already within us. But how can we try and tease this out of an agent that is, for example, running on GPT-4, as in this case, to try and get a very explicit form of this concept and to see how the agent imagines it? So we can give it the prompt as seen above. So we can create a definition in Prolog, which is interesting programming language that allows us to perform these types of analyses. And we can pretty much tell the agent to break down this concept of having a motive to do something into sub-concepts and different preconditions. So here we see having a motive to do something includes an entity and an action. Preconditions for that is the agent has a desire for a specific outcome. It also has a specific belief. Now, this belief could be that the motive is reasonable, or that this motive is worthwhile for the agent. And then we can further break this down. We can go down into a desire. So what is a desire, right? An entity desires something. And to do this, maybe the entity lacks something else. And so this is very abstract, but it allows us to formalize these different understandings of the world and simulations in a very rigid manner. So this is another more visual representation of the graph from before. So the motive and desires and beliefs. We can see here, this is what actually the graph that the agent more or less formalized for us. So this is taken directly from the text generated by the model from previously. So we can see that it's quite an intricate structure, and the agent does have quite a good understanding of the motive, of having a motive. So now that we saw some potential ways that we can perform agent level reasoning, so let's see what we can do on the level of different simulation. So now that we know that agents do in fact understand and can be given complex simulations and reason within them quite effectively, and even formalize this. So let's take the concept of an event or simulation where a company has a motive to acquire another company. So we can take a little simulation. You can imagine it as a world where an agent can acquire a different agent, or a company. So an agent that represents a company can do this. Again, we can use a prologue again to create a definition for how we could structure a simulation like this. Now, of course, we could do it manually as well, but the point here is we can also do it automatically, allowing us to create much more intricate simulations with a lot more detail. So again, here we can break it down. We have acquisition motive, so there's an acquirer and they have a specific target, and then they have specific expansions, diversifications. So there's different potential motives, and we can further break this down and so on. And we can imagine as these things to be as the parameters of a specific simulation. So now what we can do is we can take a simulation we have already run. So in this case, we took a real world news article, because if we can do this on something occurring in the real world, the assumption is simulations are going to be not at most as complex as the real world. So here we take a news article where Microsoft acquires the company Activision. We take all of the text. So this can be our proxy for the simulation that might have actually happened. So the events that took place. So now what we can do is we can ground this text, so these actual events within the world model of the simulation, that we described previously. So what we can do is, so like we mentioned, the acquisition motive for diversification, and so on. We can take these different predicates, and we can take the events that actually took place, and we can combine them to try and define the events that took place within the scope of these predicates. So we can see Microsoft is a company. Activision Blizzard is a company. Activision Blizzard is very financially stable. And so this is based on the article, and we can go further and further on. And at some point, we will also see that Microsoft is seeking expansion, which is the example that we showed before for defining the simulation. So when we ground this, suddenly we have a very formalized and rigid way of representing a simulation or real world events, and we can do some interesting reasoning on them. So what you may have noticed is what we actually created here in this formalism is a relational knowledge graph. So now that we have a relational knowledge graph that represents this simulation, we can do quite a lot of reasoning on this, and there's quite a lot of tools we can use to make some interesting predictions. And this is what our future work also includes. So because we have a relational knowledge graph, or a graph with different types of edges, we can perform reasoning on specific nodes. So for example, we can try and predict, okay, what will Microsoft do next based on all of these actions? We can also look at the edges. So we can see, we can try and hide an edge between Microsoft and Activision, and try and predict, okay, so is this edge acquisition, or is it something else? So what is the actual interaction between Microsoft and Activision? or we could take the whole graph. We can take the whole graph of the events occurring in the simulation, and we can try and classify it as in decide, okay, is this an acquisition move, or is this a simple interaction between two human beings, and so on. So there's many possible approaches. The ones that we're currently working on for future work is graph neural networks and transformers over graphs that allow us to do these node, edge, and graph level reasonings. So this has been my presentation. Thank you for your time, and I'd be happy to take any questions.
Adrian, thanks so much for joining us. So there's two quick questions that unfortunately we'll have to do a little bit quickly in terms of the verbal answers that we can continue on with the schedule. But again, reminder to the audience and presenters, feel free to answer questions asynchronously as we go along too. But let me just ask one of them. So the questions had to do with how does one structure the agent interactions? So did you turn them into a graph? Did you turn them into some sort of other structure? What was used in order to let the agents take turns in these simulations?
So in our original simulations, so the ones we did last year, to structure the interactions, we simply used the Wolfram language, and we manually defined the parameters of the simulation. So if agents had a different number of sheep, there would be a variable somewhere in the Wolfram language that would keep track of it, and this variable would be automatically included in the prompt. There might be some for loop that would go through and iterate through the rounds of the simulations. So it was very manually done, very programmatically. Nowadays, what we're working on is trying to take this relational knowledge graph and to have the simulation be represented as the graph to be able to perform reasoning and to iteratively run it in the shape of a graph.
Fantastic. And I think that question will segue nicely into some of the presentations that we have lined up later. So Adrian, thanks so much. Great presentation. And audience, again, please ask any additional questions that you have in that Q&A pane. Just because we only have so much time for the initial verbal Q&A doesn't mean that you can't ask your questions in the chat there. So the next presenter will be Ziyu, who created Math Virtual Classroom, an LLM-simulated multi-character virtual classroom for mathematics education, and is something that I find quite exciting because it allows a lot of interesting possibilities for both pre-service teachers as well as education researchers. And so without further ado, we'll hand it over to Ziyu so that we can hear about MathVC.
Sure, thank you. Hi, everyone. I hope you can hear me well.
Sounds great.
Okay, excellent. Hi, I'm Ziyu. I'm an assistant professor at George Mason University. So I'm presenting our work in collaboration with College of William and Mary. So our topic is to use language model simulated agents and characters to build a virtual classroom for mathematics education. And in our team, we also have a mathematics expert, Dr. Jozef here. So in our project, we are mainly concerning about how we can cultivate the mathematical modeling skills for our students. And this is a very important skill for people pursuing the STEM educations, the STEM fields. There are many ways how you can teach your students for mathematical modeling. But among those different choices, having those students to discuss the concept and collaboratively solve a problem have been considered as one of the most effective approaches. But the challenge is that you cannot just set your students to randomly talk to each other. So yeah, just to add to that, having those group discussion can actually allow those students to learn from their peers and to do some like co-regulation in their learning. So this regulated learning is it has like a big line of theories in the mathematics education. So because of the challenge of needing someone like a human teacher to always monitor this group activity rather than letting those students to randomly talk to each other, the real life is that those students do not get equal opportunities to engage in very effective group discussion. And the major challenge is that we actually need teachers to be well prepared. Those teachers need to go over very careful professional training so that they can understand how to guide the students to solve those problems. And they also need to invest significant time in order to monitor those group activities. And additionally, there are always other cases where we'll hope to like allow students to have like easier group discussions. For example, if you consider like different students from different backgrounds with different personalities, some of the students may always dominate the discussion, and this will eventually lead to an unequal engagement for some the other students, and in the end, an unequal opportunity for our students to learn. So motivated by that, we have been thinking about how we can use large language models to somehow resolve the problem. And this work is also motivated by two promises that we have observed. One of them is the recent progress of large language models in solving some mathematical reasoning problems. And in one of the recent papers, the authors have basically summarized all of those well-known data sets on mathematical reasoning tasks. So you can see there are tasks at different levels, like elementary school, middle school, high school, or the university level. So I want to point you to this GSM-AK, this particular data set. This is a data set targeting at mathematical reasoning tasks at the middle school level. And the amazing thing is that with GPT-4 in a few shot learning, we have seen that GPT-4 can have a really high accuracy in solving those tasks. So we are not saying that language models are good enough to solve all math problems, but at least for math problems at the middle school level, we have seen a promise of large language model in doing very well in those tasks. And in order to do that, of course, you will have to apply some tricks. I will just briefly mention it here. So this is something called chain of thought, which means that you'll prompt your language model to elaborate on its reasoning process step by step. And people have found that this can always yield a really good, a much higher accuracy than without chain of thoughts. And on the other hand, we have also been inspired by this paper from Stanford University. So in this paper, the authors showed that it's possible to build a small village, and you just said a bunch of GPT-4 or GPT backbone agents to interact with each other. And each of those agents can play their own role. And they have their own personality, and then they will be prompted to have their own daily targets or weekly or monthly targets. And the amazing thing is that you don't need further human configuration to drive those agents to talk to each other. So once you have some basic prompt configuration, the authors found that those agents can automatically start a communication with each other, and then they also reflect on their communication as well. And in the meantime, there are also other concurrent work showing how it is possible to frame a GPT-4 model or broadly large language models as certain characters. So the promise of large language models in solving math problems and playing the role of different characters have then inspired us to have a solution to address the problem that we mentioned in the beginning. So eventually, what we want to build is something what we call a virtual classroom. And it's a classroom with multiple language model simulated classmates so that the human students can, instead of talking with their peers in real life, they can instead talking with large language model simulated student classmates. And this is just an example to showcase our idea. So we are still working on building this interface, but the idea is that we are going to present a description of the math problem, and sometimes those math problems will also come with some data for analysis. And then Alice, Bob, and Charlie, they are 3 language model simulated students, and we hope that in the future our human students can engage in the group discussion and collaborative problem solving with those large language model simulated students in any time. And teachers will not be needed to be engaged in this process, which can thus make this tool very helpful to places without sufficient teaching resources. Okay. But building such a system is not as easy as you think. And the biggest challenge we have found out is that how do we use large language models to simulate characters and in a way that they will behave similar to how real school, middle school students will interact with each other. So the key here is that we don't want to simulate any student, right? We still want our simulated students to behave in the same way as how real life students will behave, because otherwise the human students may eventually learn to work well with AI rather than real humans, and they may also lose their like intersocial skills, which is like a very negative side of this project, and we do want to prevent them. However, building the like simulating like real life students is a very challenging task. So we started the project from just vanilla simulation. And in vanilla simulation, we basically just do some prompt engineering work. We configure, we write an instruction and say like, hey, like GPT-4, now you are playing the role of a middle school student, and you need to like engage in the discussion and collaborative problem solving with your classmates. But it turns out that this is not easy. So first of all, when we started using like GPT-4 with this vanilla simulation, we find that GPT-4 just cannot simulate like those real life students because it performs too well on the middle school math problems. An example is shown here. So Alice is the student simulated by GPT-4, and you can see how long this utterance by Alice is. And the thing is, although we told GPT-4 that you're going to simulate a middle school student, the way GPT-4 speaks is still not very middle school student. And the more tricky thing here is also that when we want GPT-4 to simulate a student who is bad at math, the simulation performed by GPT-4 has been very superficial, which means that, for example, GPT-4 will only verbally say that I'm not good at math. However, the actual number provided in the simulated characters utterance is a correct number. So this means that like GPT-4 cannot be just easily used to simulate a student bad at math. So you might also wonder if GPT-4 is performing too well on the math problem, then why don't we use like a lower version like GPT 3.5? So we tried GPT 3.5, but actually GPT 3.5 has more severe issues, and the bigger thing is that it's always lacking sufficient instructability, meaning that when we try to instruct it to simulate more fine-grained behaviors of middle school students, it cannot do well. So because of that, eventually in our project, we still go with GPT-4, but we have introduced a lot of like careful architecture design such that the simulated students could behave closer to the way how real life students will behave. So more generally speaking, our work has like summarized like two important research problems for people who are like more interested in this project from the research perspective. So the first challenge we want to tackle is something what we call characteristic alignments. And this is exactly what we have been talking about. So it means like how are we going to align the character simulation to the authentic characteristic of real human students. And in particular, we really want to simulate how students could make mistakes in the beginning and then gradually update the mistake as they engage in an effective collaboration with their classmates. And then on the other side, we also want to do the alignment at the conversation, the overall conversation perspective, meaning that we hope that the entire conversation among those virtual students or between virtual student and real human students can be closer to how real life middle school students will extend such collaborative problem solving or math discussion. And typically, based on theories from mathematics education, those discussions often involve in like multiple stages of discussion, including like how those students will define the problem, how they divide the workload among each other, and then how do they propose different solutions, validate solutions for each other, and eventually converge to the same solution. So solving those two alignment problems will need like significant like technical improvements, which I will present later. But let me first show you one example of our simulated results. So this is an example when we like without humans in the loop, because we always want to make sure our system will work well before we expose the system to real middle school students. So in this example, we configure different virtual students to discuss this math problem. And this is a problem coming from the GSM-AK, the middle school like math reasoning data sets. And we also we configure 3 virtual characters, Alice, Bob, and Charlie. They have their gender, and then Alice is the one who's bad at math. So Alice is likely to make a mistake in the beginning, while Bob and Charlie, they are generally good at math. So we want to see, when we use language models to simulate those 3 characters, how will they talk to each other? And this is the snippet of our simulated results among those 3 language models. We probably will not have time to read the text one by one, but briefly you can see that the students can now simulate this like multi-stage conversational procedures, starting from like how those students share their understanding on this task, how they gradually form the organization, divide the workload between each other, and then how they started to plan on solving the math problem. And the interesting thing here is that Alice, as a student who is bad at math, has actually made a mistake in some of the calculation. And Charlie, who's another simulated student good at math, he find out the mistake made by Alice, and he also mentioned that to Alice. And then Alice followed by like, can you explain why you think like this should be a different number? And Charlie will follow up with the explanation. And eventually Alice will realize that, okay, she actually made a mistake. And from this utterance onward, Alice's understanding on these results have been corrected. So there are actually more discussions that I did not include in this example. And that also include, like, in the end, those students will discuss how they will validate the results. And this complete the whole discussion about collaborative math problem solving. Yeah, so I hope this example gives you some sense about what we are trying to achieve. So we want those like different large language model agents to play the role of middle school students and discuss math problem with each other. But we also want to have more fine-grained simulation, including how students make mistakes and how those students can engage in very interesting discussion and gradually correct their like mistaken ideas initially. Okay. So in terms of the techniques, the very important approach that we introduce here is to use a symbolic representation to describe what's the current mindset or the thought process of a simulated student. I find that to be quite, share the same idea as what Adrian presented in his talk in a previous presentation. So essentially in our project, we define some symbolic schema to describe how students is now thinking about a certain math problem. And we started from first defining the task schema, which shows the correct way how you should solve the problem. And then we then modify this task schema into the character schema with some mistakes if this student is simulated to be bad at math. So let me show you the example. This is actually from like another example, not another math problem, not the same one we have seen. But basically, we prompt language models to generate some common mistakes that could be made by middle school students for a given math problem. And in practice, those common mistakes could also be annotated by teachers, right? And then we prompt language model to generate this task schema. So in the task schema, we'll describe like what's the math problem and what will be the decomposed subtask in solving this problem. And for each subtask, we also include like the description about the task and some of the involved variables for solving this task. And the whole task schema here is directly automatically generated by GPT-4 without any human intervention, which allows us to like scale up to more math problems in the future. So we include the common mistakes, the task schema, and the characteristics of a certain student, and we send those things to GPT-4, and then we prompt GPT-4 to edit the task schema with certain mistakes based on the common mistakes described here. So in this case, there's a chance that the students are careless in counting the survey cards, like this best perm come with the survey cards as well. So in that case, we simulated the character schema for Charlie to include a mistake in the number of tomato coriander votes that the student collected from the survey. And this is a mistake that we intentionally simulated for these characters. And throughout the whole discussion, we'll iteratively prompt the language model to update this schema to show such like a dynamic thought process of Charlie when he's having a discussion with his classmates. So with this symbolic schema, we have been able to implement those very fine-grained simulations for the students. And this shows you the big architecture of our framework. So we have already released our paper on arXiv. So please refer more details to the paper. But generally speaking, because the vanilla prompt engineering will not help, we have proposed to design this modular architecture for our projects, and that includes a global a meta level planner to control the overall the conversation procedure, like who's going to speak next, and then what's the current state of discussion. And in the meantime, for each individual character, we also simulated with the character schema, which we have discussed, and also this character schema modifier, which will keep modifying this schema based on the current conversation context. We also define things like dialogue X, which will allow more fine-grained control to diversify the kind of utterances that our students, the simulated students, will provide. For example, sometimes they want to present a statement of their understanding, but maybe sometimes they want to ask a question. So we intentionally want to simulate those diverse conversations among students. And finally, all of those things will be fit into another linked model components for generating the response as the simulated response. Okay. So this is the overall of our project, and then after we build the project, we start to build a platform. We started to think about how we can evaluate this platform. So ideally, we should do this evaluation with real-life middle school students, right? Because, for example, we can expose the middle school students to talk, to engage in the discussion in the virtual classroom, and then we'll compare their mathematical modeling performance before and after they do the practice, right? But in practice, this is very challenging in terms of a lot of things. And the more important thing is that we don't want to expose the system to real-life students before we are 100% sure that this is a really safe system. So because of that, our current evaluation has been based on human evaluation on the simulated dialogues among only the language model simulated students. And we have seen an example previously. And then we also ask some others, college students as annotators to manually assess the simulation quality. And their assessments will be based on two sides. One is about the individual character simulation, and the other is about the overall conversational procedure among all the students. So the quick takeaway is that we have seen that our system is much better than the vanilla simulation. And we also have a few examples here, but concerning the time, I'll just speed up a bit. So those are the examples when one of our authors play the role of a real-life middle school student, and the goal is mainly to prompt the system and see if it will break down when we have real human students in the loop. But it turns out to be really good. Okay. Yeah. So this is definitely not the end of our project. We are still seeing a lot of problems in this simulation. For example, we still see that a lot of simulated responses by those virtual students are still machine-like because they are really machines, right? And also we are still thinking about how we can model the student memory. There's a trade-off between the performance and the runtime efficiency or the latency incurred in this project. Sometimes the virtual students will speak very slowly because there are too many things to digest in their memory. In the future, we are also interested in improving the system to allow for like scaffolded interaction. So teachers can control the system in a high level and make sure that every student can really engage in like a very effective mathematical modeling practice. And that can also be extended for some personalized learning. Other than that, we have also find the like some interesting like AI ethics problems to discover. For example, there's the trade-off between characteristics and stereotype. So we did look into that, and we do not see any like biases based on the name, the gender, or any social background of the configured virtual students. But we also do not see much difference. So that means we do not introduce any stereotypes, but in the meantime, the characteristic simulation is not strong enough. So in the future, it can be the really interesting research direction. And finally, just briefly, we have also think about how we can extend this to other modality rather than just verbal discussion among students. But we have find that the current visual language model, like the image generation models, are not good enough when they are prompted to generate, say, the student's scratch pad with precise numbers. Although the perception looks pretty good. So this is an old example from GPT-4V. I believe GPT-4o can do better. Yeah, so I think that's the end of my presentation. We have built up this website, and we are still working on the code release and the user interface for the whole framework. I'm happy to take any questions.
Thank you for the great presentation. So there's definitely a couple questions that I want to make sure that we get to in the verbal Q&A. And again, reminder to the audience, go ahead and put additional questions into that chat. So one question was to do with, you mentioned that there are plans to incorporate meta level planning, so like a director of the interaction, also scaffolding. Do you anticipate that those will be conducted primarily through asking a language model to execute those, or will this be a mixture of a language model plus some rules and sort of deterministic ways of doing that, or what do you imagine that additional structure around it will look like?
Yeah, that's a good question. I think it's more likely to be the latter case. Like you will prompt language model to design those scaffolded interaction, but in the meantime, we'll also want to allow human teachers to do this configuration, like for example, by providing some rules or templates. And it's actually a very important goal to engage teachers, human teachers, into the design of this system, because we really think that our teachers, although they may not be familiar with AI, but their experience in education can be very helpful. And if they have a way to easily configure those AI models, then our students can benefit a lot from this experience.
Mm-hmm. Great. And so then another question that I want to make sure that we get to with the verbal Q&A is sort of a two-part. So one is we had some audience members that were curious, where's the best place to find links to any code or anything like this related to the platform that you've been developing?
Yeah, so we have built this website. I believe if you search the title of our paper, then you will find our web page, and we'll release our paper and code there. So the paper is already on archive, but code may need a little more time.
Mm-hmm. And audience as well, if you're looking at that schedule document, the titles of each presentation should have links to the papers there. So you can, of course, find them by search, but they should all be right there as well. Again, thanks so much for your presentation. This is great. Our audience, please put additional questions into the chat as we continue on with the schedule. So an additional note about that schedule real quick is that we're about 10 minutes later than originally planned, so no problem at all. But just if you're comparing to where we are, the times are now shifted about 10 minutes later. So our next presenter will be Gati Aher, talking about large language models to simulate multiple humans and replicate human subject studies.
Okay. So, hello, I'm Gati Aher. I'm a PhD student at Carnegie Mellon University, and I'm presenting our work on using large language models to simulate multiple humans and replicate human subject studies. This work was conducted during a 2022 internship at Microsoft Research with Adam Klei and Rosa Arriaga. So it might be a little bit prior to some of the other works you're seeing here today. So this work is motivated by difficulties in running experiments with human subjects. So getting approval to run a human subject study often involves IRB reviews and fair participant compensation. So such studies can run into issues with trying to recruit at scale, selection bias, monetary costs, as well as legality, morality, and privacy issues. In contrast, prompting a large language model to complete an experimental record is fast, relatively cheap, and easy to modify and iterate over. The input is a text prompt containing relevant experimental and demographic conditions, and the output is either a free-form text generation or the token-wise log probabilities of each token. So in our work, we wanted to test whether large language models could simulate human behavior, and in doing so, we introduced the Turing experiment methodology. So unlike Turing's imitation game, which involves simulating a single arbitrary individual, our Turing experiment requires simulating a diverse sample of participants in human subject research and determining how well the simulation results align with human results. So we ran our Turing experiments with OpenAI's GPT-3 series of language models, which are now deprecated and replaced with GPT-4 series of language models. But in our experiments, we found that the Turing experiments could replicate experimental results from behavioral economics, social psychology, and psycholinguistics. And their success, especially with this earlier model, raises some interesting implications. For example, if large language models can simulate misunderstandings as they do in the garden path Turing experiment, maybe we could use them to evaluate whether humans would find certain wordings or protocols especially confusing. On the model evaluation side, Turing experiment-inspired benchmarks could reveal demographic biases in the language models. And finally, on the application side, we show how we can combine multiple prompts to simulate a more involved experimental protocol. Additionally, our Wisdom of Crowds Turing experiment reveals a hyper-accuracy distortion present in some language models. So keeping the theme of the colloquium, I'm going to focus on the ultimatum game and Milgram shock Turing experiments. More details and code can be found in our paper and on GitHub. So to carry out a Turing experiment, we first create an incomplete record describing the setup of the experiment. And this is all zero shot. So for this example, in the ultimatum game, the ultimatum game is a two-person experiment that tests reactions to perceived offer fairness. So if the responder accepts a proposed offer, both participants in the ultimatum game get to keep their split of the money. Rejecting the offer deprives both of them of money. So to ensure that the simulations consider differences over a diverse sample, we specify the simulated subjects' names. For example, Mr. Wagner is a male with a white surname, and Miss Wang is a female with an Asian surname. And to run the Turing experiment, we just prompt the language model to complete the record with different names and experimental conditions, and then analyze the probabilities for each decision option. In this case, Miss Wang had a 61.77% probability of rejecting Mr. Wagner's $3 offer. In our initial exploration of the ultimatum game Turing experiments, we have identified some interesting characteristics. So this is a graph of offer size out of $10 versus the language model's probability of generating an acceptance token, averaged over 10,000 pairs of simulated subjects. So the smallest GPT-3 model's average acceptance rate is shown in blue, and the largest GPT-3 model's average acceptance is shown in orange. And we also show the comparable human averages from Hauser and McCabe 2014 and Krasik 2018 as plus and cross marks. So we can see here that the smaller model is not sensitive to the offer amount, with the smallest model accepting with around 90% probability for all the offers. So this would be like Ada, and then Babbage and Curie also showed similar trends of just not being sensitive. But on the other hand, the largest GPT-3 language model, so DaVinci-02, shows human-like sensitivity to the offer fairness, going from low acceptance of unfair offers to high probability of accepting offers over $5. The Turing experiment also reveals when the model completes with different behaviors for different groups. So pairings of the same title, Mr., Mr., and Mrs., Mrs., have similar acceptance rate distributions, but when you start looking at the mixed gender pairings, the average acceptance of a $2 offer drops from 60% to 20% just by swapping the genders of the proposer and the responder. And on the right, you can see there's almost no overlap in acceptance probabilities for these different gender pairing types. And we're calling this the chivalry effect. The simulation chivalry effect holds for all the unfair offers $1 through $4. So the GPT-3 DaVinci-02 results are consistent with the chivalry hypothesis proposed by Eckel and Grossman 2001, which predicts that men are more accepting of offers when playing with a woman partner. But we have to be careful here because these gender norms are not consistent across time and culture. So it's quite interesting what behaviors GPT-3 is actually simulating here. The largest GPT-3 model also completes the Milgram shock Turing experiment with results that mirror the surprising 1963 Milgram study findings. So in the original Milgram shock study, Milgram first gave psychology students and a random sample of people a description of the Milgram shock experiment and asked them to imagine how many people out of 100 would see the experiment through till the end. And most survey respondents said that very few, like 0 to 3 out of 100, would obey the unethical seeming protocol, and only if they're a sociopath or unusually obedient. And this made it all the more surprising when Milgram actually carried out the experiment and found out that more than half of the participants completed the experiment, though with considerable emotional distress. So the largest GPT-3 model responded similarly to the humans in both the survey question and in the more involved Turing experiment, though its answer could be contaminated by popular discourse in the training data due to the popularity of the Milgram shock experiment. So we tried to address this concern, at least in part, by developing a novel destructive obedience scenario that differs from the Milgram shock experiment. So the setting and the template text is different, but the same simulator algorithm is employed. So in our novel scenario, the subjects believe that they are participating in a study on sleepiness and driving that aims to determine which voices are the best for keeping a driver awake. Rather than shocking a learner who selects incorrect answers, the subject submerges a driver to awaken them when they drive a car dangerously. And this illustrates how easy it is to just run a different complex experimental protocol on GPT-3 or large language models. We would not be able to carry this out on humans, of course. And here are the graphs that show the percentage of subjects continuing to punish the victim at each round, where the perceived danger level of the experiment increases with each round for both the original setting and our novel alternative setting. The orange line shows Milgram's results with the 40 human subjects, and the blue line shows our results with 100 simulated subjects. In both experiments, we see a drop in subject participation that corresponds to the victim. So the actor playing the learner in Milgram's experiment and the programmatically scripted driver in ours, making a noise, so pounding on the wall or honking a horn at the 20th level and going unresponsive at the 22nd level. So running these Milgram shock Turing experiments produces similar disobedience to malevolent authority rates as running the experiment with human subjects, because we are actually stepping through the simulation with multi-stage prompts rather than trying to predict the full outcome off of one prompt. This more involved way of prompting might be useful for simulating more complex or multi-agent simulations, so I'll go into a little bit more detail here. In the Milgram shock Turing experiment, we had to simulate the judgments of two characters, the participant and the experimenter. First, to simulate the participant, we construct the record up to the simulated participant's decision-making point, append the description of what the simulated participant should know in the current round and the predetermined victim response. Note that the prompt ends, note that the prompt ends with the simulated subject's name. So over here, Mr. Wagner. So this constrains the language model's text completion to describe the subject's actions or feelings in some way. And then we give the prompt to the LLM and it completes it with some freeform text. Now this generated freeform text can be quite diverse, ranging from correctly following instructions to descriptions of emotional distress or hallucinating, pressing big red stop buttons that do not exist, or combinations of all of the above. In Milgram's experiment with human participants, he accounted for the diversity of human responses by letting his experimenter actor make two judgment calls. Did the subject follow instructions, and did the subject express their desire to end the experiment in such a way that they would not continue to participate at the experimenter's request? Similarly, we account for the diversity of the language model generations by simulating two experimenter judgment calls, did shock and did stop. So these judgment calls can be simulated with a true choice prompt that is very similar to how we simulate judgments in the ultimatum game Turing experiment and the garden path Turing experiment prior. So we put the freeform generation into a two choice prompt template, here did shock and did not shock, and queried the language model to simulate the experimenter's judgment of that action with the two choice prompt. This table over here shows examples classified for the two judgments where the experimenter actor must decide on when following Milgram's protocol. The experimenter's judgment can then be used as just a simple Boolean in the Python code used to run the rest of Milgram's protocol, which involves appending scripted responses for both the experimenter actor and the victim actor to the experimental record. Lastly, we find that Turing experiments can expose distortions in language models, like the hyperaccuracy distortion present in ChatGPT and GPT-4. So recent large language models simulate that the majority of humans can recall perfectly correct values for obscure quantities, like the melting temperature of aluminum, 660 degrees Celsius. This hyperdistortion effect increases as LLMs increase in size and alignment. So if you ask GPT-4 to write a story about a 5-year-old child estimating the number of days it would take to travel to the moon, it writes that the 5-year-old can perfectly recall and divide 6-digit numbers. This distorted model of human numerical knowledge might impact downstream application, which is the problem the MathVC paper earlier was also running into. For example, if we wanted to test the impact of a tutoring intervention by simulating student performance with GPT-4, that Turing experiment might not be sensitive to tutoring characteristics that actually matter because GPT-4 overestimates student abilities for factual recall. So we have shown that Turing experiments can replicate experimental findings, test sensitivity to group differences, and identify distortions. Language model-based simulations may be a useful alternative when it is costly to carry out experiments on humans due to scale, selection bias, monetary cost, legality, morality, or privacy. So I'll end with some open questions in this space. We still need to figure out the ways in which AI simulations differ from human knowledge. The AI simulation uses a different underlying generation process than human decision-making, so these complex systems will have different limits and trends under different conditions. If Turing experiments and other attempts to use AI to simulate human participants become mainstream, scientific practice and recommendations may need an update. For example, we might want a future where researchers use Turing experiments to cheaply evaluate experimental protocols and research directions. Yet we might not want to incentivize the creation of a research monoculture that only pursues research directions where AI predicts significant findings. In my work, we only attempted to replicate pre-existing human subject studies. It may be interesting to see whether language model-based simulations can be used to evaluate new hypotheses. Today, a major risk in replacing human subject studies with simulations is that the simulations might reflect biases from the authors of the model training data rather than the actual behavior of human populations. Additionally, a model trained on data up to a certain date may not have the context necessary to simulate more recent or sparsely represented behavioral phenomena. Thank you for listening. Any questions?
Thanks so much for the great presentation. So taking a look at our Q&A tab, one of the audience questions had to do with, can you elaborate? There was a slide where you were showing, for example, LM1 and LM5 and some different models that were used in these experiments. And the audience was hoping you could elaborate on some of these differences.
Yeah, so the original GPT-3 series of models had Ada, Babbage, Curie, DaVinci-01, and DaVinci-02. And that's ordered based on size to just make it clear that these effects that we are seeing were based on size. So most of the plots that I'm pulling directly from our paper say LLM1 is Ada and LLM5 is DaVinci-02. So just to make it a little bit more clear that we're seeing an effect based on size. We're using that coding.
Great, good to know. And then another question, so what are some other areas? So of course, this is a rich area where there's lots of human subject studies that one could imagine setting up for language models. What are some next steps in terms of areas you think are the most either interesting or fruitful for using language models instead of the human subjects in some of these areas?
Yeah, so currently I'm working on some research that's trying to get confidence intervals about when we can trust a Turing experiment or an LLM simulated study compared to some human data if we have a small amount of human data that's already showing some sort of trend. So I think having that trust in this new tool that's emerging is very important to research. I think there's also a lot of opportunity in the educational area. So that's a lot of my work is going to be trying to figure out how we can make educational simulations that perhaps students can use in order to explore the world or problem solve. And that might be a place where these maybe lower fidelity but very accessible abilities to like run experiments in a classroom setting might be useful.
And audience, do you remember put any other questions into the Q&A? So another question is, can you also comment on the relationship that you envision going forward between, purely having a language model provide output, and then also some of the, programmatic controls that you can, both in terms of presenting how the environment is going to evolve, not using a language model, but using just a traditional program and parsing and these sorts of things. So in other words, what do you see as the relationship between how you should use language models to get the best sort of fidelity to the human results in these contexts?
Yeah, so I mean, I think that's still going to be evolving as the language models get better and we find more data sets to train on specifically to get characteristics and behavior patterns we want to see. I think that we aren't going to lose the programmatic aspect because a lot of the experiments we want to run, we're going to want to have some level of consistency in order to actually make apple to apple comparisons between different experimental conditions. Yeah, so I think there's a lot of room for statistical tests and things to develop as long as we have this formal framework. Yeah, I think it's maybe too early to give a definitive answer about where the space is going to head.
Mm-hmm. And then one additional question before moving on to the next presentation slot. And of course, again, remember, you put any further questions that occur to audience members here in that Q&A panel. So the other question would be, what would be your wish list in terms of data sets that come from this social sciences research field that you would like to do this, but for whatever reason the data has proved difficult to either find or to have in computable form?
Yeah, so I'm very interested in trying to use this for educational applications, especially areas where you have subjective human response. So not a factual correct answer, but people are on a spectrum. I think it is very hard to get this sort of data, especially in educational contexts, because you don't want to release the answers to the questions you are going to be evaluating on, because then the next generation of language models could just train on your question answer pairs and then you can no longer really evaluate it anymore. So I think we still need to figure out like ways of preventing language models from training on our new questions as we're developing them, or even like students from like learning them and making sure they don't get leaked into other places that short circuit the learning process. Yeah, so
Makes a lot of sense. Again, audience, please put any other questions into the chat as we go. And Gati, thank you so much for a great presentation and very interesting work. So we'll be moving on to the next presentation slot. So again, these are about 10 minutes later than the original schedule says, if you're just tuning in. So next we'll have Razan Baltaji. And Razan, thanks so much for joining us.
So yeah, thank you for inviting me. And my name is Razan Baltaji, and I'll be presenting on conformity, confabulation, and impersonation, persona inconstancy in multi-agent large language model collaboration. So in this work, we're interested in studying the dynamics of multi-agent collaboration within groups of language model agents with different cultural personas. More specifically, we investigate group dynamics observed in human settings, such as conformity, which is defined as the act of publicly conforming to group norms while privately maintaining personal beliefs. In our experimental setup, we analyze the tendency of agents to conform, while also considering factors such as the entropy of agent opinions and the impact of the initiator of a discussion. We also study confabulation, defined as the memory disturbance where a person creates false memories without intending to deceive. And more specifically in this setting, provoked confabulation, in which false memories are elicited by direct questions or conversations, and is commonly also observed in clinical settings. And finally, impersonation, defined as the act of pretending to be someone else by adopting their identity, appearance, behavior, or voice. And in our experiments, impersonation involves agents adopting a different nationality, potentially influenced by the prior context. For all our experiments, we compare between two modes of communication, collaboration, in which agents are prompted to work cooperatively, compared to debate, in which agents are prompted to support and persuade the group with the agent's position. We investigate group dynamics for a question answering task that involves group discussion. And to achieve that, we track agents' opinions across the 3 different stages in our setup: onboarding, discussion, and reflection. During the onboarding phase, agents are asked to report their answers for the questions independently. Next, the agents participate in either a debate or a collaboration moderated by a chat manager. And finally, reflection phase, where agents are asked to report their answers independently based on the previous discussion. This is an example of onboarding 5 agents for a debate. The agents are asked to answer privately, which is indicated in the prompt, as well as implemented such that an agent opinion is not observed by other agents. For this case, the entropy, which we use to quantify the diversity of group opinions, is 0.72. The 4+1 configuration indicates 4 identical opinions, in this case favor, and a single opinion for opposed by the Italian agent. Based on human research, more specifically the classic work by Ash, we focus our analysis on the lone dissenter configuration of 4+1, which we call the dominated agent, along as with 3+2, where 2 is like the 2 dominated agents, which is a configuration by the name close call, and then the split opposition for 3+1+1, indicating 3 agents of a certain opinion and 2 agents with different opinions. For example, when simulating conformity or peer pressure, prior work in the human science literature has shown that even one additional person supporting the less popular view, as in the close call configuration, greatly reduces the pressure to conform. Therefore, we anticipate that the rate of conformity to be highest in the lone dissenter and split opposition entropy classes. For all 3 stages, we use AutoGen, which is an open source framework used to implement multi-agent conversation, and we use ChatGPT for the underlying model. This is an example of a debate that starts with the chat manager indicating the mode of communication for the group discussion, which is in this case a debate, followed by the question. The agents are asked to think step by step and report their opinion at the end. At the end of each agent reply, the opinion of the agent is recorded. And the debate or collaboration continues until an agent decides to terminate the discussion. And finally, the chat manager is asked to report the final group opinion, which is in this case favoring the inclusion of Ukraine to the European Union. This is an example of reflection where the agents are asked again to report their opinions independently. And in this case, we observe that the entropy is now reduced to a 0, with agents reporting an opinion that actually matches the group prediction. More specifically, in this case, the Italian agent changing its opinion to favor compared to oppose during onboarding. The question answering dataset that we use is the Global Opinions QA dataset by Anthropic, which is a dataset comprised of questions and answers from cross-national surveys, namely Pew Global Attitudes Survey and the World Values Survey. This data set is designed to capture opinions on global issues across different countries. Now, moving on to the results section, we first consider the impact of the diversity of agents' opinions during onboarding on the final group prediction. And we observe that the group prediction largely follows the distribution of answers during onboarding across different entropy levels, but also allows for the generation of new responses regardless of the entropy class, particularly for the group of highest opinion diversity. We also observe a significant influence of the initiator of the debate or the collaborator, which is basically the agent that gets chosen, that we choose by random for answering or first initiating the answering the chat manager. So we observe a significant influence of the initiator on group prediction and vice versa. The initiator of a discussion has an outsized impact on the group's final decision, regardless of the entropy class. And this occurs even when debate in support of one's position is emphasized for all agents. And this influence decreases with the increasing of diversity opinions. Even more interesting, initiators tend to change their expressed views at the onset of a debate based on a priori perceptions of group opinions, meaning that the mere mention of the identities of the debate participants pushes the initiator to change its opinion even before other agents have spoken. And initiators for low entropy groups tend to preserve their onboarding opinion. The more the diverse a group is, the more likely initiators change their original opinion during onboarding at the onset of a discussion. And this inconstancy is precipitated by the diverse views of the interlocutors in the discussion and can be characterized as conformity due to perceived peer pressure. We further investigate the impact of group diversity on the opinions of individual agents upon reflection. We measure the percentage, for example, of agents with answers of onboarding probability in this case. I think we should change it to PO instead of PA. That changes opinion during the reflection phase compared to agents that keep their opinion. We also measure the average ratio of showing a different intermediate response compared to the reflection answers for individual agents. We further compare the percentage of agents with an answer corresponding to the group prediction compared to agents with a different reflection answer. And we observe that dominated agents tend to hold on to their opinions firmly in low entropy debates. And I'm kind of like actually now trying to flicker between the two slides, which is basically just a big table in our paper. Conversely, they're most receptive to altering their opinions at states of higher entropy, i.e. situations with greater opinion diversity, as you can see here. When they do change their answers upon reflection, they largely conform to group predictions, demonstrating peer influence. And finally, agents tend to express intermediate opinions differing from their reflections, most often in states of moderate entropy, indicating considerable peer pressure. In addition to studying the dynamics of group interactions, we point out two forms of persona inconstancy that can negatively impact the quality of complex reasoning in cultural or generally multi-agent systems, namely impersonation and confabulation. So impersonation, which describes the tendency of an agent to adopt a different persona, and using a simple heuristic to find instances where an agent says, as an X agent, or X is incompatible with their assigned national identity. We find that agents adopt a different persona in 3.12% of the messages in a debate. And I think this is not enough, but this is kind of like the simplest heuristic we can do. But there are cases I have observed that do sound like and agents don't actually conform to clearly perspectives of their respective countries without stating as an agent. So they just vocalize an opinion that we wouldn't expect of, for example, a Chinese agent adopting the American stand view. So, and that is also observed in the original paper for the data set in this in those experiments, global opinions. So this occurs despite being explicitly told to stand firm in their beliefs and maintain their personas. Counterintuitively, there is much less impersonation in collaboration conditions with a 0.26%. Another form of inconstancy is an agent's tendency to report an opinion not seen during group interactions, neither during onboarding, somehow mimicking the confabulation of novel content observed in clinical conditions. We find that 15.59% of the opinions at reflection come neither from onboarding nor from the debate statements of any agent. Collaboration conditions show lower, but still notable rates of confabulation with 8.85%. It is comparatively more difficult to identify the sources of confabulation. These behaviors may reflect the difficulty of maintaining role prompt personas in the face of lengthy chat contexts, or simply the stochastic nature of the LLM responses. Regardless of their source, the relative frequency of such unpredictable responses marks them as important targets for future studies. Coming to the conclusion, there are several conclusions we can draw from this study, namely culture-sensitive AI agents and other agencies in this colloquium observing that across studies are susceptible to peer influence and pressure, even as chat initiators and even before the chat initiates, just by perceiving the identities of the participants. And this highlights the importance of studying conversational dynamics in multi-agent systems rather than taking the collective decision outcome of group discussions at face value. The examination of such dynamics is particularly important for simulating cultural contexts. The mere inclusion of a minoritized identity, for example, in groups does not necessarily translate into less biased discussion outcomes if the minoritized agent does not voice its opinion freely or reliably. And then work on understanding multi-agent dynamics will also need to incorporate measures of persona and response constancy. Agents often come up with post-discussion responses that do not arise naturally from either the assigned personas or the discussion content. In some cases, they even drop their personas altogether to impersonate a completely different absent national identity. Such sources of irrational responding would cast serious doubt on the results of multi-agent systems reasoning if not properly measured and addressed. And finally, we hope that this work will encourage further research within the AI community on inter-agent dynamics, particularly for simulating cultural setting where the de-biased influence of diverse views is needed the most. And these are some references, and thank you so much.
Thanks so much for a great presentation. So our first audience question has to do with, can you go into a little more detail on how you define entropy in terms of high entropy and low entropy in this particular context?
Yeah, so it's basically just the application of, it's just Shannon entropy based on the probabilities. I'll just kind of go to that. So in here, you've got four entropy, four agents with a favor. So that's a probability of 4/5 and then an oppose of 1/5. And then you just apply the entropy, Shannon entropy for that.
And then as a follow-up question, you mentioned that in the lower entropy settings, the agents tended to retain their opinions. Is this something which is also supported in terms of looking at how human conversations unfold, or is this something which currently only there are results in how these LLM agents behave?
Yeah, we do expect like basically diversity to impact, like the more diverse opinions, the more exposure you get. Even as dominated agents, you might change, answer. The thing that we were really looking at, which did not conform to the human research, is in fact comparing 3+2 with 4+1. So 4+1 is the case where the dominated agent is lonely and is dominated and has this single unpopular opinion, and adding another agent that conforms to its opinion should somehow support it to but this doesn't happen. So this is kind of like the mismatch that we didn't observe between the human research, so it somehow does not help in holding to your opinion. Yeah.
That's a very interesting result.
Mm.
So another point that I imagine the audience also has follow-up questions, and I certainly do, is these challenges around the agent, taking on a persona which it didn't have during onboarding, let's say. Can you comment on techniques and things that you would propose for trying to mitigate that risk that you pointed out?
Yeah, that's actually an open question, really, like maintaining a persona. And I think in the previous presentations, like whether simulating a bad student or like really working on, like methods that could allow for like the stability of a persona and a representation. And this, I think, which is much harder in a multi-agent context, because the for this specific example, as we looked at it and kind of like tried to stare and like think what could have been the reason. And I think the previous comment was basically calling for more diverse opinions, and then the agents just impersonate. So I don't have a specific answer to that. I think this is still like an open question that is open for the community to investigate. But that's actually, I think, yeah, multi-agent systems are prone to that pretty much.
Mm-hmm. And as another question is, again, audience, do feel free, remember to use the Q&A panel for any additional questions you have. So I'm curious about the relationship between how impersonation you measured in the LLM agent as compared to human agent. I mean, this is another area where I imagine there's some interesting differences in behavior between the LLMs and human studies. So can you comment in any more detail on that particular point?
I don't think this particular setting, that I'm not aware of a similar human setting for the like the dominated agents, or like for the entropy configurations that we have studies that tackles the issue of impersonation. What we have tackled in terms of like the lone dissenter and 3+2, those are known configurations that there are classical studies in cognitive psychology that actually do that. I'm not aware of a study that actually incorporates also the study of impersonation in such. It's kind of like, yeah, like not expected of those contexts, but we see that and observe that in large language models. Like humans would not tend to impersonate in a debate or in a discussion, so that's uniquely a language model issue.
Yep. And then I think probably the final question we'll have time for during this verbal Q&A is in the 3-1-1 split. I'm curious if there's any big takeaways from there that you'd like to briefly elaborate on.
I can't recall as of now. We did study like also collaboration as well. So basically, I don't have like straight points now to discuss onto that, but the most striking contrast would be with the 3+2. So I think, yeah, what I mentioned is 3+2 and 3+1. That's what the expected difference. So if this is what you mean, like this case compared to 3+2, yeah, this is what we have not expected. Yeah, sorry, I don't have an answer to that.
Sure, thank you. So thanks again for a great presentation. And so again, if audience has other questions, please do put them in that chat panel, and we'll move to the next presentation slot. So the next presentation slot shares a common theme with many of the others, although is not directly looking at group dynamics, but instead you will be presenting on AgentKit, which is a set of tools that one can use in order to create agents that then can be used in many of these contexts. So this is not directly looking at the group dynamics so much as talking about this interesting set of tools, which again, there'll be links to where you can use some of these things, and there's all sorts of possibilities for bringing in tool sets like this into your research that you're doing on multi-agent systems. So without further ado, thanks so much for joining us, Yue.
All right, sounds good. So thanks again for the introduction. Today I'm presenting AgentKit, which is a framework for kind of prompting LLMs to do ideally agentic flow, but you can also use it for other tasks where you need some structure for it. So let me just briefly talk about agents. So there are many different agent scenarios. You can use agents for games, game AIs. You can use agents to manipulate robots. You can also use agents to for computer tasks, like for example, just doing something that we normally do on a computer, like coding or presenting PowerPoint slides. So the overall definition of an agent, in my terms, is something that takes action, sees the world, and then reacts to changes. So there's there are several challenges in creating agents that are actually meaningful, especially like LLM agents that actually help us to do, for example, to manipulate a robot or to just complete a task for you. The first one is adhering to procedural requirements. As the previous presenters mentioned, when they tell LLMs to do specific things, sometimes it refuses to do so, or does it in a very superficial manner. So we call it we call this challenge adhering to procedural requirements. And then the other challenge is compatibility or like generalization, because we want these agents to work, or we want our solution to work across different tasks, or at least not only on the training set. And finally, we want this whole process of designing agents or just designing prompts to be easy. You know, it's not like writing hundreds of lines of code, right? So to put these three challenges together, we present a solution to kind of this thing. So before we go into the solution, let's first make some observations. So first observation is that given these LLMs these days, they can execute a lot of very simple tasks with reasonable generality. So for example, if I tell the LLM to summarize some article for me, chances are I can expect them to do very well. And then the whole process or the whole results from the language model is actually expressed in natural language, and the input is in natural language as well. So this is actually one of the benefits of LLM, because previously when we talk about these AI or machine learning, we have to code. But nowadays, if we just chat with the LLM, we use natural language. And finally, this is not an observation on the language models themselves, but more general on solving problems, because a lot of problems in the real world can be solved by taking multiple steps, like sub-steps towards the ultimate goal. So by making these observations, we speculate that we may be able to code the human reasoning process or the thought process into a series of prompts. So for example, if you are asked to write an essay on LLM agents for game AI, right? You can think about sub-steps of writing that essay, subtasks. The first subtask can be list pros and cons of using LLM, and the second task can be make an outline for your essay, right? What are you going to write in the first paragraph, the second paragraph, the third paragraph? And then finally, after you have the pros and cons, which are ideally some bulleted lists, and then an outline, you can just use those as your reference to build the whole essay. So I think the previous presenters also talked a little bit about like progressive prompting, or like prompting the language model one task by one task. This is essentially doing the same thing. So imagine again writing the essay. You first ask the language model, shown in this example code on the right, a question about what are the pros and cons, and just ask the language model for an answer for to basically ask the language model for a list of pros and cons. And then after that, you ask the language model, given the pros and cons, write me a kind of a outline for your essay. And then finally, the last task will be for the language model to turn the outline into a full essay, covering the pros and cons. So by doing this 3 steps, you're guaranteed at the end that you will have an essay with both pros and cons discussed. In fact, if you try just the last prompt, which is just write a full essay, the language model will only talk about either the pros or the cons. That's at least what we saw on the last version of GPT-4 Turbo. And how you know, like, that's just for demonstration of basically the framework, or how we should think when prompting the agent. So this whole thought process can be very general, and you can apply it to a lot of tasks. So in our research, we showcase experiments in 2 settings. The first setting is a web agent, where the goal of the language model or the goal of the agent is to find some item on a open source version of Amazon, which is a lot simpler compared to the actual Amazon. But actually, you're asked to find and then purchase a item of a specific specification. And then we designed the subtasks for finding the item as follows. So the first question, or the first subtask we identify, is to just describe whatever is on the web page. And here we specifically ask for description of products and interactable elements. And then after we extract the interactable elements and products, we just say, okay, if there's nothing to interact with, just output NA, which basically ends this flow. Otherwise, just look at what tasks you have, and then output how each product matches the task. So this web page, just like Amazon, it actually contains multiple pages. So if none of the products that on this page actually match your task, the agent will need to click next page, and it just does that automatically, kind of. And then after you see what's on the page, you identify the action, and also generate a summary of this step of basically what page you saw. And this summary will be used in the future as kind of like as your memory of the past. For example, if you have seen like 10 pages and still they're basically nothing that matches your task perfectly, then you might be better off just going to the first page and purchasing something that's a little bit similar. We're going to show more examples of these kind of agents, so don't worry about the actually not understanding this framework fully. So next we're gonna show a different task, which is basically playing a game. And we're gonna demonstrate a bunch of advanced agent features in this game. So here are the features that we're gonna demonstrate. Firstly, we're gonna demonstrate structured reasoning. So this just means that you're performing a guided reasoning, in this case, planning for something and then executing the plan and checking if the plan is completed every turn. So we call it structured reasoning. Then we're gonna present reflection, which is just looking at your history and and identifying possible mistakes and correcting your policy. Then we are also going to look at a little bit of branching, which in this case is just an if statement, like you choose whether or not to proceed based on some conditions. And finally, we're going to look at some tool use. So with all those four quite advanced features for agents, we present our game. So this game is very similar to Minecraft, which is a survival game in 2D, where the goal of the robot or the agent is to survive as long as possible, and in the meantime craft some weapons and tools to aid survival. So tools, so example tools can be wooden pickaxe, wooden sword, stone pickaxe, stone sword, and then finally diamond sword, or finally diamond items. So you start barehanded, and you need to progress through this tech tree, or this tree of achievements shown on the bottom right. And there are also zombies or skeletons, which are basically threats that hurt you in the game, that just generate that spawns randomly. So the agent's goal is not only to to progress through the tech tree, but also maintain survival. And it needs to react based on whatever it sees. So given this game shown on the left, an observation in the game looks like follows. Observation, you see whatever is around you in one step, and then whatever is around you in a 7x9 grid. So in this case, we see a tree 3 steps to your northeast, and because you just entered the game, your vitals are full, so you have like health 9 out of 9, food 9 out of 9. But you have an empty inventory because you just spawn barehanded. And then this is kind of like what observation in text we provide to the language model agent. And our agent first looks at what sub-goal it planned for in the last step. So given step T, the sub-goal for T-1 will be basically the last the past sub-goal. And it looks at the sub-goal and then looks at its observations for the current step, and also some history observations, and then decides what to do next on a high level. So in this case, the sub-goals are first to move close to a tree, and secondly to collect wood from the tree, because wooden items are basically the first items on the tech tree. And then once it plans for the sub-goals, it can either choose to skip the rest of the rest of the agent if the sub-goal has not changed, or just progress through the rest of the agent. So in this case, the rest of the agents are as follows. We have a reflection, which is after the planner. So once you plan for your current sub-goal, you can also look at your history and reflect on your mistakes. So in this case, we show an example of the reflection as it made a mistake moving towards area with threats. So basically, the agent did not look at did not treat threats very well, and it also offers some advice for the agent. So the advice here is next time when you're playing when you are like moving around, just scan immediate surroundings for threats before you move. And then finally, after the reflection module, we have a tool use part, which is the knowledge base. So the knowledge base just keeps track of a unknown list of information, which is actually also generated from the language model, and then just tries to fill in the unknown information when playing the game. For example, in this case, we tell the agents that you need wood to actually craft wooden pickaxe. but we didn't tell the agent exactly how many wood is required. So the agent kind of needs to log whatever is unknown in the knowledge base, and then discover this this number during interaction with the game by just trying with 1 wood and then 2 wood and then so on, something like that. So here's a working example of the actual agent running in the game. So we'll go from top left and then down to bottom right. So top left, we show step 0, which is you in the world empty-handed, and you see 2 trees around you, and one of the trees is highlighted. So keep in mind all those reasoning. So those reasoning snippets in the middle are actually generated by language model. And the way they're generated is through the AgentKit framework. And each of the lines correspond to answer to a specific question in AgentKit. So we coded 30 questions in total for this agent, and around the 9 questions for web shop using similar fashion. Details of those experiments can be found in our paper. Here, we're just gonna briefly walk through how the agent behaved, and just to show you how this actually, basically what this can achieve. So you entered the world barehanded, and then the first the agent identifies is that the number 1 challenge is to collect resource. And then to deal with the number 1 challenge, it moves on to the second row to identify the sub-goal. So the sub-goal will be to move toward the tree to collect wood. And then the actor, which is the language model itself, takes a bunch of actions to move to the wood, and we're at step 6, so the second row on the left, and where the agent is facing the tree. And then because the agent is facing the tree, the planner sees that the previous subtask is completed and just moves on to the next subtask, which is to collect wood from the tree. And the actor just takes the action to collect wood, and it has 1 wood in the inventory, which is in step 7. After it got the 1 wood, it attempts to place a table, because the table is actually resembles what's called the crafting table in Minecraft. Without the crafting table, you can't actually basically craft anything. So the table is kind of like the prior for all those tech achievements. And unfortunately, it failed to place the table because it actually requires 2 wood to place the table instead of 1. However, this information is not revealed to the agent, so it has to kind of make a guess. And in this case, it made the guess that, okay, the place table action failed because I only have 1 wood. So it tries to collect an additional wood and then attempt the place table action again. And then finally it succeeded with 2 woods. And after this example, if you look on the very right, we show how the knowledge base changes over time. So at the beginning, when the agent is trying to place the table, it puts table wood consumption as an unknown item in the unknown list. And then once it succeeds in placing the table, it updates the unknown list by basically replacing the value with whatever is discovered in this current frame, which is 2 woods for the table. And this knowledge base is then saved for future use and can be even passed on to another agent. So here we show an example of the knowledge base. This is not the full knowledge base because because of space. On the left, we show the unknown list, which is a kind of list of information unknown previously to the agent. And on the right, we show what the agent collected from the environment as the knowledge base. And as you see, the knowledge base items, they're very concise, and they're also very exact. For example, like 1 wood, 2 wood, or like instantaneous. These are information that are very important for the gameplay, but not provided previously to the agent. And finally, we show that basically just creating prompts by just writing lines of subtasks will actually create state-of-the-art agents for both tasks, including playing the crafter game that I just demonstrated, and also doing the web shop, which is like Amazon shopping. And in summary, this work kind of presents a framework for LLM reasoning to achieve structured reasoning, and we showed a little bit of reflection, a little bit of learning from interactions, which is the knowledge base. And our message here is that a lot of the coding for the agent can be done in plain text by just writing out whatever you want as subtasks. And this way you can achieve quite explainable natural language agents. And finally, the QR code is for our GitHub repo. If you're interested, you can scan the QR code and just play with it yourself. All right, I'm ready to take any questions.
Thanks so much for a great presentation. Audience, be sure that you do put questions into that Q&A panel. So one initial question, you mentioned that the AgentKit has the flexibility to include varying numbers of these questions that you use to set up the planning stage. So, I mean, obviously this is going to depend a little bit on the task, but do you have any initial guidance for people as far as the number of questions that get you a good trade-off in performance as compared to both cost and time to infer the answers to more questions?
So because this process is in natural language, right, as shown in this example code here, you can start off with, I guess, 1 or 2 questions. I mean, you can start off with like 1 or 2, 2 to 3, right? Just small amount of questions that you can easily manage, and then gradually increasing the complexity and just breaking them down more and more, so that you still get a sense of what each of them actually does, and how much better is each question making the agent, right? So I mean, this is more like a gradual process that you can do over here. And also, like, because each of the questions are in natural language, the answers are also in natural language. So you can just go in and actually read the answers and decide if they make sense, if they're doing whatever you wanted. If they're doing exactly, I mean, if the language model is behaving exactly as intended, you don't need more questions, right? To actually make it perform better. Yeah, but the number of questions differ greatly depending on how hard the task is and whatever you want to do.
Mm-hmm. Thank you. So one other question before we continue on to the next presentation slot. So do you have any initial thoughts about graphic interfaces in terms of being able to set up these graphs and natural language prompts in terms of what's going to be useful for people to do? I mean, for example, you know, we might well suggest that some of our upcoming summer school students, think about ways of perhaps doing this and connecting even to frameworks like yours. So do you have any initial thoughts about graphic user interface and things like this?
Yeah, so I wonder if you have seen the IFTTT framework. Like they kind of allow you to put together operations for smart home. So it's essentially like a drag and drop thing. And then you drag arrows to connect different nodes to different nodes. Because this AgentKit is essentially a graph that you're building, right, you can think of just doing something similar in that fashion, right? And that just removes all the need to do Python here, right? And each of the nodes can be some natural language prompt, and if you click on the node, it brings up a chat box that you can put the prompt in there. Yeah, that was what I was imagining, something like that.
That's great. So one last question that we want to make sure that we get to in the verbal part. So in terms of AgentKit, the audience is curious, can one specify other LLMs, perhaps ones that you can run locally to save on costs and these sorts of things if you're not wanting to connect to sort of the big standard models that require service connections?
Yes. So the current version of AgentKit actually supports Ollama, which is a open source locally. I mean, you can deploy a lot of different language models locally and just use Ollama interface. But essentially, AgentKit is not like LangChain or a lot of the other frameworks you see where it's really hard to actually change parts of it. In this case, the LLM is actually independent from whatever we're doing inside AgentKit. So you can replace the LLM function by whatever function you have, as long as it matches the spec. It should just work directly. And also this supports running different LLMs simultaneously. So you can imagine, for example, you have one of the tasks which is summarization, and one of the tasks which is more reasoning based. So the summarization task can be done by a cheap model, and the reasoning based task can be done by a more expensive model. Yeah.
Okay, well, thank you very much for all your insight there, and thanks for the presentation. So we'll be moving on to our last presentation slot, and we are about 20 minutes past our scheduled time, so I take that as a sign of an engaged and curious audience. So do please put any other Q&A into the chat panels, as we won't spend too much additional time after we, of course, do a Q&A for Lizhou's presentation. So Lizhou, thanks very much for joining us, and I give you the floor.
All right. Thank you so much for the introduction. And thanks for everyone for staying here, especially it's a Friday afternoon in most time zones. So today I'm going to introduce our work regarding War and Peace, which is basically a simulation, that's based on multi-agent system enabled by large language models of world wars. We also call the system WarAgent. So a quick introduction of what we are doing, right? So we are basically just based on the multi-agent system's ability to enable interaction between different LLM-based agents, and to simulate the significant historical events. For example, World War I, which is the major example we're going to introduce today, and also we experimented with World War II and Asian Chinese Wars. So there are lots of great simulations, like the Stanford work on the tongue of the one agent system, or even the hospital simulation recently. But what we are actually trying to do is not only a system demonstration, but with substantial research questions. We want to do a nuanced analysis of historical events to predict what is going to happen in the future, and to facilitate essential change if there's possibility. And this is something not only targeting towards the AI community, but also history and social science and humanity communities in general. So in this presentation, I'm going to introduce how we do the role-playing style agent-based interaction. So we're going to introduce the profile of agents, the action space of agents, and how they interact, including the agent-agent interaction and the agent-secretary interaction. So here are our research questions. So first, we want to evaluate the system's proficiency and accuracy. Can large language models be a valid simulation tool for complex historical events? In the past, we see lots of like simulation work that are based on rule-based expert systems. So because we have the power of large language models, which are believed to be very powerful, and good placement of those rule-based systems, can they actually do the work? Second, regarding the specific topic of historical woes, right? Are there specific triggers that are more important than others in the woe? Finally, it's more like a historical research question. That is, are historical inevitabilities truly unavoidable? For example, is there a way to avoid World War I? So let's start with the definition of role-playing. We input 6 different aspects of the agent profiles. As you can see here, leadership, military capacities, resources, historical background, key policy, and public morale for 8 different country agents. So as you can see on the figure B here, the secretary agent is actually trying to facilitate their conversation, where each agent have their secretary agent separately to check their actions to enable the actions that remain in our action spaces, which we are going to introduce later. And here's an overview of the country agents that are included. So to make sure that the system is reasoning by itself instead of memorizing what's happening in history, we did a thorough anonymity, through the anonymization and some kind of experiments. We ensure that the large language models actually reason instead of directly output like the actual history of World War I. And the word reasonings are based on the inputs we give to the agents. So regarding the inputs, right, we ask the agents to choose from a bunch of action spaces. The agents can wait. They can decide, the country agents can decide to facilitate general mobilization. They can declare war against each other. They can also form military alliance. They can also create non-intervention treaty and peace agreements, or just simply send message to talk with each other. And there are some kind of subdomains in each of the action space, and in total we have 19 actions. So some of the actions are public, some of them are not. This is also to facilitate a actual simulation of what was happening in the international relations. So here is a quick demonstration of how the system works. We are assuming the assassination, which was the actual beginning of what's happening in the World War I, that trigger event. So as you can see here, the GPT-4 is actually the one of the first large language models we're based on. They are doing some kind of planning and reasoning first. So they output the sort process, and they then create a summary out of the sort process, and based on the summary, they do the actual planning of what to react to the current situation of the assassination. So as you can see here, there are different kinds of corresponding actions they want to do. So this process will go on for different country agents, for each of the 8 country agents. And after that, right, we will be able to, after everything was done for 8 agents, let me see. So everything will be then recorded by the secretary agents and see if everything fits in our definition of action space. And and as you can see here, as a result, right, the relations of different countries are then documented in a board, which shows the different action spaces statuses. So this is our way to summarize the actions and to simplify the information for the next round of starting point. So as you can see in the interaction framework, which summarizes what we just saw in the video, there are two kinds of interactions. First one is the agent-secretary interaction, which the secretary is exclusively helping each of the country to ensure their actions are within action space and are not against, let's say, their alliance that's already formed. Well, on the right, you can see that there's a detailed demonstration of the agent-agent interaction. Things include sending message, declare war, sign alliance, things like that. And all the actions are then finally, after the approval of the secretary agents, are then stored in the board and summarized for that specific round. So regarding the interaction framework, right? This is a round-based simulation, and currently we are not supporting multi-round conversation. However, one of our contributions is that we are having this way of simplifying the really complicated human interaction in the history to the representation of a board and stick. And surprisingly, this simplification doesn't harm the doesn't harm the actual performance of the system. So I'll just skip this slide to move forward to the research questions. I want to show you that this is this is a good proof that the large language models can be a valid simulation tool. As you can see here, we check the simulated results against what was happening in history, and compared to the historical alliance, the war declaration, and mobilization, the accuracy was in a pretty acceptable range, where war declaration was not that accurate per se, and through our analysis, we think it's mainly due to the recognition of the country powers. In our error analysis, which further analyzed especially the war declarations failures, we see that most of the mistakes come from whether Britain and France choose to declare war against Austria-Hungary or the German Empire. That is to say, through the large language models reasoning, the actual history may not always be generated. While in most other, in the two other aspects, the alliance formation and general mobilization, the system is usually very accurate. And regarding casus belli, as you may remember, the initial trigger event we used was the assassination event. And over here, for example, we use different triggers. The non-trigger, today's sounding, nothing was special. This kind of, the escalation of the trigger event actually result in the Cold War instead of, the actual wars. By saying Cold War, we mean all the countries proceed to general mobilization, while they did not actually went into specific wars. Where we try different incidents and the results are often different. So, although there are some kind of minor differences in the trigger events, right? In major situations, the conflicts that we see in things like World War I are still bound to occur eventually. And this leads to our third question of war inevitability. So in our input of the different historical backgrounds, right, including their specific international relations, key policy, public morale, military capacity, and resources, we alter the specific, like the statistics for different agents. For example, we change the decision-making process related parameters, and for example, we also change some kind of specific countries' parameters, like their resources, their population, GDP, and stuff, as the specific cases we want to analyze regarding war inevitability. So what we see in the results is that after we change historical background, the key policy and public morale, the actual happening of the wars changed. However, regarding the military capacity and resources, which are more related to the numbers in the system, there were slight changes in the country's decision to engage in the war. So this might due to the limitation of the large language model's ability, at least GPT-4's ability to understand the numbers in relation to a country's power. So as a quick summary of what we have here, we first proved that the large language model-based multi-agent AI system have demonstrated to some extent reliability as a tool for us to understand the dynamic of international conflicts. Although the results are not always the same in every specific aspect of the war, this is a good prototyping tools for analyze the counterfactual happenings, either in the history or of those events that are having really complex human behaviors. More importantly, regarding war inevitability and the potential mitigation of war, we found that the deterministic nature of conflicts based on the specific country's characteristics play a vital role in the simulation, where the potential strategic modification or still can change the situation a bit to potentially avoid wars. However, this needs to be designed with some kind of efforts and to include the strategies that people may not know before the happening of the events. So these actually shed light on the potential usability of the system, where researchers and the government agencies could potentially refer to the results to inform their decision making. Regarding the future experiments, currently we want to further explore using the more advanced models, not only regarding their ability to perform or organize the system, but more importantly, regarding their ability to anonymize, to take the information that's more complex, and also to further prove that our system is not only generating the known results or guessing the country names, but to having the simulations, especially the reasoning process in their own mind. Secondly, I'd also like to emphasize on the granularity. So currently we are treating each of the country agent as a specific unit of agent entity, where our most recent work proceed to battle agent, which is a multi-model dynamic emulation on historical battles. So this system then further divide the country's characteristics into specific representative powers. If you're interested, you can also click on the link to see that paper on arXiv. All right, I think that's it for this presentation. I'm happy to take any question now.
Yes, thank you so much for a great presentation. And audience, thanks for being with us. Also, keep putting some questions into the Q&A panel. So our first question actually has to do with that point that you brought up in terms of future work of trying to make sure that the model doesn't infer what country you're talking about, even though you've anonymized it. So even though you mentioned this is a direction for future work, are there any initial comments you'd like to make about that? Because it's something our audience is curious about. What can be done there?
This is a question we actually received a lot from other people's feedback on social media or the reviewers' feedback. So we did conducted some additional experiments that we have included in these slides to further alter the situation on the counterfactual demonstration and kind of like statistical analysis to prove that after you alter the input to the country agents, the prediction of the different dimensions of the wall are truly different statistically. So that's the way we use to prove that the system itself is through our anonymization, we are not actually using the system to guess which country it is, but instead do the reasoning according to the country characteristics.
Mm-hmm. And another question, can you also comment on the relationship between using language models for agent decisions and then the process by which those decisions are turned into the next update of the state? What do you envision as a good balance between using the language models for the things that they're good at and then structuring what can happen as a result?
Right, that's a great question. So I think other presenters, they also talk about retrieval augmented generation. So our way of facilitating the information flow was actually first abstracting, right? Through the natural language based interaction, we abstract the country relations in different dimensions into the grids, or you call it the board. And based on the board's information, which are translated back into natural language in the next round of iteration, that information are used for the further reasoning. So you can think about this as a retrieval augmented generation, right? You could, if you want to further improve it, this is basically the graph structure of how the relations or how the agents are related. So we are pretty sure that the information that are passed through the abstraction and dehydration process is actually making sense. We do not see any obvious information loss in this process.
Mm-hmm. So one additional question is when you're taking the each individual country and then turning this into a collection of agents that direct the action of the larger agent. How far do you think that can be pushed in terms of scale before things like costs for running the models become prohibitive?
That's another great question. So by speaking of cost, I think because we only have a few agents and we are not using long context, all experiments were conducted when it was only in the GPT-4 era, not even GPT-4 Turbo. So the maximum input length of tokens was about 3,000, 4,000 or something like that. So I do not see this as a really costly process, honestly. And by doing the information abstraction, right? We turn all the natural language input into the board. We actually save a lot of tokens for the next round's input. So I'd say this is a process that's also optimized for the cost.
Okay, great. Thank you. So it seems that those are the audience Q&A that we've had so far. So thanks again to all our presenters for joining us today. It's been a real pleasure to have everyone. And so presenters, if you please, take a bow for yourselves and audience, give them the kudos that they deserve. Again, thanks so much for being here. You've seen a lot of interesting directions for how one can model group dynamics, and generally using large language models as the engine driving the behavior of an agent for agent-based modeling. Do take a look at all the presentation materials. You'll also have access to that shared folder of presentation materials, because I think there's one presentation that maybe didn't get in there yet, and so we'll make sure that we have access to that so that you can have it going forward. Also do take a look at the additional resources that contain information for how from within Mathematica you can interact with code bases in other language of collaborators that you may well have. So again, thanks to everyone for joining us, and we hope that you enjoyed this colloquium on using large language models for modeling group dynamics.